We'll conclude BST 611 with a review of the course objectives and a discussion of additional methods that were not covered in this course. So we'll look at topics that we covered, how those related to our course objectives, and what else is there in statistics that hasn't been covered in this course. We've done data analysis using all of the methods of categorical methods for proportions and continuous methods for comparison of means and correlations. We've looked at both large sample and non-parametric statistical tests and how to report these results. This covers a tremendous amount of what is done in statistical testing. These are often referred to as what are called preliminary analyses or univariate analyses. So we're looking at most two variables, a single X and a single Y. We started the course with 9 objectives for BST 611. Each of the modules supported one or more of the course objectives. For the first course objective, for applying descriptive techniques commonly used to summarize public health data, we spent a great deal of time talking about how to report sample size information, how to report proportions, means, and medians with ranges or interquartile ranges. We talked about the difference between standard deviation and standard error. For course objective 2, in describing the basic concepts of probability, random variation, and commonly used statistical probability distributions, we spent a great deal of time on how to assess the probability of events occurring. If those events are independent or mutually exclusive, if they are conditioned on another event. We learned how to utilize known distributions to calculate p-values, which is also the probability of observing our results or results more extreme. That led us to objective 3, which is distinguishing among the different measurement scales and the implications for the statistical methods to be used based on these distinctions. So we had categorical, which were nominal or ordinal. That then implied that we had to utilize methods to assess proportions. We had continuous variables, either interval or ratio. We also looked at proportions or percentages as part of continuous measures. Those would lead to comparisons of means or a correlation or relationship between two continuous measures. That led us to looking at more specific common statistical methods for inference in objective 4. That's the z-test, chi-square test, t-test, f-test. We also looked at multiple comparison tests called Tukey's HSD and Pearson's R, which was really a t-test for your correlation, and then also the inferential method of confidence intervals. Objective 5 dealt with when those common situations were not applicable, generally when the assumptions were not met, the assumptions of large sample size, the assumptions of normality, or the assumption of equal variance or homogeneity of variance. The non-parametric tests we looked at were exact binomial or Fisher's exact when dealing with proportions. We looked at Welch-Zanova for unequal standard deviation tests for means. And when non-parametrics didn't hold for mean tests, we used the Wilcoxon, Mann-Whitney-U, or Kruskal-Wallis test. There is a multiple comparison test for medians called the Steele-Dwas, and we could also utilize a Spearman's Row summary statistic and associated test for ranked correlations. For all of those methodologies, in objectives 1 through 5, we talked about how to display the data via tables, charts, and graphs to convey an easily understandable method or easily understandable results. Use always real column and row headings and real axes labels, not your variable names from your software. Always edit your output to useful percentage or limit decimal places to be consistent. Justify your tables in a consistent manner and stick with a useful and large enough font and lines and figures to be read by your reader. Objectives 1 through 6 can also be assisted in being met with Objective 7, managing our data sets and selecting the appropriate approach to analyze your data. Review your variable types, missing values, outliers, and errors, and your distributional assumptions. And then this will help lead you to determine which questions you can and cannot answer and which statistical tests are most appropriate. Once you've run your statistical tests, Objective 8 is about interpreting the results of those tests found in public health studies. We learned how to make statistical decisions for well-defined hypotheses based upon p-values. And Objective 9 was to communicate the results of statistical analysis to both biostatisticians and non-biostatistician public health researchers. The most important thing here is to put your results in words with context of the question. Convey your differences in terms of the measures that you observed, and interpret the statistical results for the reader. If you are clear and concise, the reader will walk away with the message that you intended. The question was well defined, you applied appropriate statistical methodology, you determined if there were any important differences or results, and reported those results in a meaningful manner. What we've covered so far in all of the modules and the 9 course objectives does not cover all statistical relationships and tests. We have not covered the following situations. A response that is categorical with a continuous predictor. We didn't look at 2 paired proportions. We haven't talked about time to event, also called survival analysis. Those data are often very skewed, and not every individual has had an event or has not died yet. So we could have incomplete information called censoring. And how do we deal with that? What about the relationship between more than 2 categorical variables? What about nonlinear data or S-shaped data? What about pharmacological models or nonlinear models? What if we have a continuous response, but we have more than 1 predictor variable? Or some predictors are continuous and categorical? What about multiple correlation or multiple regression data? And what about if we're only interested in testing for agreement? So we have 2 raters or testers who are rating the same measure on the same thing. How well do those agree? What about genetic, environmental, and individual sources of variation when independence assumptions are not met? How can we use measurements there to classify objects into a structure, a nested structure, or a taxonomic structure? We'll address a number of these questions in BST 612. It's important for you to know at this stage you have the ability to assess your data for sample size and distributional assumptions and do simple univariate or single X and Y tests. Beyond that, you'll need to learn the assumptions associated with modeling or multiple predictors. That comes in BST 612, and a number of the other more advanced methodologies you'll learn in BST 613 or in your own individual statistical education. The bottom line is we want to use easy-to-use or user-friendly software, and we encourage scientists to do much of their own simple analyses. And this is fine. You've had a solid education in the foundations of these methods, but there are limits, and you will run into roadblocks where you need to seek help. Do that. Find a statistician, find a consultant, or continue your education on your own to branch out beyond the methods you've been taught here. Most importantly, we've seen the importance of context, how data are collected, and how this determines whether the numbers are useful. We've also talked about pervasive issues associated with variability and randomness, and how that colors the interpretation of our data and our results. Statisticians can phrase questions in a particular way, and it's a fundamental way of asking, could this data have arisen by chance? What it generally boils down to is if we want to know if this group is different from that group. We assume a current state, and we want to know if our observed data gives us evidence to the contrary. If it's a plausible interpretation that random variability is what we're observing, then we'll go with the simple-minded explanation or the null hypothesis. If chance explanation is unlikely, we see a small p-value, then we'll choose a more complex explanation, the alternative hypothesis. None of this is definitive or an ironclad cause and effect interpretation. Remember, we are choosing to believe the null hypothesis and looking for evidence to the contrary. We do not prove anything utilizing statistics. We only provide sufficient evidence to conclude either the null or the alternative hypothesis. Statistics is one part of the scientific method, one important tool used in the scientific quest for understanding. It's a simple process and is simply a way for seeing. There is no one right way. You need to select a way and justify your choices. We've seen many tests that are applicable in multiple situations. If you follow the 10-step method and apply what you've learned in a systematic way, that will help you answer your scientific questions. Thank you for such a great semester. I urge you to continue with your statistical education either through coursework or on your own, and wish you the best of luck with your final exams.